CERN has made headlines yet again. The renowned Laboratory for Particle Physics has announced a rather unprecedented discovery made by their Large Hadron Collider that may likely cause a shift in our understanding of the universe. Scientists have reported that these anomalous readings could signal the existence of extraterrestrial life in a parallel universe. In this video, we will be discussing the just-announced CERN discovery that changes everything. In a recent experiment with the Large Hadron Collider, CERN scientists noticed something strange with a particular kind of quark. Quarks are the building blocks of all matter and come in different types, which physicists call flavors. Some of these so-called flavors of quarks were extremely unstable and decayed rapidly. The subject of this particular anomaly was the beauty quark, which has an average lifespan of 1.2 trillionths of a second. It turned out that the quark's decay pattern was radically different from what scientists predicted based on the standard model. According to their predictions, when a beauty quark decays, it should be influenced by the weak force and transform into what is called a lepton, which is a set of lighter particles, either an electron or a muon. The standard model predicted a 50-50 chance for both particles, but what the data from the Large Hadron Collider was showing was relatively different. The data showed that these quarks decayed into muons only 70% as often as they decayed into electrons. This was especially attention-worthy because electrons and muons are carbon copies of each other. The only difference is that the muon is 200 times heavier. Still, it should not affect the rate of transformations. All the forces within the standard model are supposed to pull on these two particles with equal strength, and because the beauty quark decays through the weak force, both should result from the transformation the same number of times. There is only one way for this anomaly to occur: if a new type of particle that has never been seen before gets involved with the process. Some researchers have speculated that some new type of physics could be at play. A new force-carrying particle should mean brand new physics, which could expand the standard model and answer many unanswered questions. The possibility of new physics. Currently, we do not have many ways to probe particles, so the theory of the standard model is our best understanding of how the strange world of particles behaves. The standard model is a scientific framework that describes everything we know about the building blocks of the physical world with pinpoint accuracy. But the shocking thing is that even with this relatively high level of accuracy, physicists are well aware that this model still needs to be completed, and plenty of pieces still need to be added to the reality puzzle. Out of all the fundamental forces, the standard model can only describe three: the electromagnetic force, the strong force, and the weak force. Currently, it has no description of the force of gravity and no explanation for the dominant form of matter in the universe: dark matter. During recent experiments, researchers noticed an anomaly within the data they were analyzing that did not correspond with what is known within the standard model. Even though it is not generally uncommon to find results outside this model with the sheer amount of data that the LHC produces, this time, however, something has caught the attention of scientists, and they knew they needed to take a closer look to discern this new phenomenon. What could this new force be? What could this brand new force be? To explain this unprecedented discovery, the researchers have considered that there may be a new fundamental particle, which they have called Z prime, a brand new force-carrying particle. Even though this force is more than likely to be extremely weak, because there have been no signs of it until now, according to the researchers, this force would interact with electrons and muons in different ways. But the extent of its interactions with the particles of the standard model remains a mystery for now. This would be a breakthrough that physics has been waiting decades for. If they found new force-carrying particles, physicists are hopeful that if this discovery is confirmed, it could help unlock established mysteries of the universe and answer ongoing questions like what dark matter is, or paint the full picture of the Higgs boson's role in creating our reality. Some scientists have come up with a theory that this unknown force may help achieve one of physics' biggest goals for the past century: to unify the fundamental forces of nature. The Large Hadron Collider and its work. The Large Hadron Collider does its best to test these theories, but in addition to that, it can speed up beams of heavy ions, especially lead ions. Proton and lead collisions are usually carried out for 1 month each year. The primary objective of the Large Hadron Collider is to allow physicists to test the predictions of many particle physics theories. It is worth noting that they are looking for the enormous family of new particles predicted by subatomic particle theories and measuring the features of the Higgs boson. Hadrons are subatomic composite particles consisting of quarks, bound together by a strong force, similar to how the electromagnetic force holds atoms and molecules together. Baryons like protons and neutrons are some of the commonly understood hadrons. The pion and kaon mesons, first identified during cosmic ray tests in the late 1940s and early 1950s, are also included. The LHC brings two opposing particle beams together so they can collide. When these particle collisions eventually occur, they result in a shower of particles whizzing out in all directions. These particles have a relatively short lifespan. Most of them stay in existence for a fraction of a second or millisecond before decaying out of existence into nothingness. By varying the types of particles, researchers can discover new particles in these flurries, with the help of specially designed technology. Supersensitive detectors are placed around the collision sites to prevent the loss of any information from every collision. This massive amount of information adds up and requires a huge amount of time and manpower to sift through. Data at CERN. The experiments carried out at the LHC can create more than 15 petabytes of raw data from these collisions every year, which the scientists then meticulously comb through to sort out the data they are looking for. The LHC achieved a significant milestone in 2017 when scientists permanently put over 200 petabytes of data into its tape libraries. To put this massive amount of data into perspective, 1 petabyte is equal to around 250,000 movies. The Higgs boson is said to be an elementary particle that is associated with the Higgs field. It is the quantum excitation of this field, similar to the way you see ripples in the sea. The boson itself is like a completely new kind of animal amid other animals in the zoo of particles. It has neither the quantum properties of elementary matter nor those of the carriers of quantum interaction, such as the electromagnetic force, weak force, or nuclear interactions. The Higgs boson was discovered at the Large Hadron Collider, a groundbreaking discovery made simultaneously by the two large multi-purpose experiments ATLAS and CMS. It was announced on the 4th of July 2012 at CERN. At the time, the new scalar boson was observed mainly in two rare decay channels, which offered the cleanest signal. The decay was observed in a pair of photons, which involved a purely quantum virtual process, and the direct decay in a pair of Z bosons, the carrier of the neutral-weak interaction. The discovery of the Higgs boson at that time may have completed the standard model, but this wasn't the end of investigating this elusive particle. One of the significant discoveries made since 2012 involved confirmation of the decay of the Higgs. According to scientists at that time, the investigation of this elusive particle will deepen during the third run of the LHC, particularly when the particle accelerator's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, providing researchers with more opportunities to spot exotic physics, including phenomena beyond the standard model. CERN has estimated that, as the accelerator is upgraded each year, it will create 15 million of these particles. This is compared to 3 million Higgs bosons created by the LHC in 2017. This may be key to detecting other flavors of the Higgs boson. Theories that go beyond the standard model of particle physics also predict as many as 5 different types of Higgs bosons, which may be produced less frequently than the primary Higgs boson. Even before the upgrades, magnetic Higgs bosons, scientists have already provided strong evidence of a magnetic Higgs boson. But what is so important about this Higgs boson, anyway? The Higgs field played an extremely important and decisive role in the first moments after the universe's birth. It determines the very nature of the vacuum that fills our space-time. It is why matter and interactions exist as we know them, and it is responsible for the appearance of the mass of all known elementary particles. Without the Higgs field, and thus without the Higgs boson, there would be no atomic elements, stars, or life in this universe. The God particle and its importance. Why is the Higgs boson called the God particle? The Higgs boson's moniker, the God particle, was strengthened upon its discovery due to popular media. The origin of this is usually linked to Nobel Prize-winning physicist Leon Lederman, who had referred to the Higgs boson in frustration as the goddamn particle with regards to how difficult it was to detect. According to Business Insider, when Lederman wrote a book on the Higgs boson in the 1990s, he had wanted the title to be the goddamn particle, but the publishers refused and changed it to the God particle. That was the beginning of a troublesome connection between the particle and religion, which still bothers physicists today. Still, it's hard to overstate the importance of the Higgs boson and the Higgs field because only particles would have mass with this aspect of nature. That means there would be no stars, no planets, and no people, something which may be a little justification for its hyperbolic nickname. Why study the Higgs boson? Why do some scientists still study the Higgs boson? Besides the obvious necessity to perform the most precise characterization of the new particle, there are two main reasons why scientists still study the Higgs boson. First, they want to understand how the physical vacuum in which we live was created in the early universe. Secondly, they want to understand how this physical vacuum can be made stable. The Higgs field is unique, providing a non-zero mean expected potential energy to the physical vacuum. In essence, this is what makes the whole difference for our universe. Scientists believe that there is a possibility of accessing the shape of the energy potential, which is responsible for the very existence of the electromagnetic force of infinite range and the weak force acting at very short ranges. To do this, scientists must study how the Higgs bosons interact with themselves. For this, they need to produce pairs of Higgs bosons. The Higgs boson helped solve the important question of the origin of the mass of all other elementary particles. However, its mass is yet to be explained. Any symmetry of the theory does not protect this mass and brings unwanted instability to such an extent that through quantum processes, the physical vacuum itself could become destabilized by quantum fluctuations. Fortunately, this is on timescales that are considerably larger than the known lifetime of the universe. But scientists are still looking for additional Higgs boson-like particles that would signal the existence of the new physics that is needed to stabilize the Higgs boson mass. All these factors motivate the analysis of much more data, and if possible, access to higher collider energies. This is why thousands of scientists worldwide are still dedicated to the task, even after 10 years. Why did it take so long to discover the Higgs boson? The Higgs boson was proposed in 1964 and discovered in 2012. Science enthusiasts have wondered why it took so long. It is because the Higgs boson is both heavy and extremely unstable. To produce such a heavy particle, the scientists had to concentrate a considerable amount of energy in a small volume. They needed a high-energy collider. Once the Higgs particles are produced, they decay in many different ways, and only a small fraction of them can be distinguished from the common background. Scientists constructed the largest and most complex detectors to identify such particles. Then, they analyzed hundreds of billions of proton-proton collision events to extract a Higgs boson signal. Could CERN have opened a dimensional portal? The question remains. Will CERN's projects and discoveries help us make bold breakthroughs, or will they send us to meet our ultimate demise? Conspiracy theorists have three popular theories regarding what CERN is really up to. The first and scariest theory, which caused people to point accusing fingers at CERN, is that CERN is trying to open a portal leading to hell. Some people believe that CERN's tampering with subatomic particles traveling at the speed of light will lead us past the gates of the ultimate fire. However, CERN has clarified that its goal for creating antimatter is to understand matter and mass better. The encyclopedia has defined antimatter to be subatomic particles with the reverse electrical charge of matter. Those who support the Big Bang theory think that antimatter was created during the universe's formation and should represent matter equally. But on the flip side, antimatter is very rare. The second CERN conspiracy theory is that of the Mandela effect. The Mandela effect is simply a phenomenon when many people remember an event from the past occurring differently than in reality. Some conspiracy theorists think CERN's particle experiments will likely cause shifts in our reality and push our world into an alternate dimension, creating a large-scale Mandela effect. Third and finally, some conspiracy theorists believe that human sacrifice happens on-site at the CERN complex. A video supposedly appeared online in 2016 claiming that ritual sacrifices were happening at CERN. The video supposedly showed several cloaked figures walking around the grounds of CERN. It was speculated that the footage captured a young girl being stabbed in the chest by the cloaked figures. According to The Guardian at the time, a CERN spokesperson came up to debunk the claim, saying that the ritual was staged as part of an elaborate prank. The question of whether a police investigation took place after that is yet to be answered. It is no news that CERN has been a long-time target of conspiracy theories, so it's no surprise that on July 5, 2022, when scientists resumed activity after 3 years of completing upgrades and maintenance, conspiracy theories would also show their faces online. While science hopefuls may find this news disappointing, it is clear that CERN has no plans to open a portal to hell, the future, or any other dimensions. Beams of protons keep whizzing around the 27 kilometers loop of the world's largest particle accelerator, more than 300 foot underground. For over a decade now, its ability to smash particles together at extremely high energy has been helping humanity peer into the virgin frontiers of physics. The Forward Search Experiment Detector at the LHC has achieved an unexpected goal. For the first time, it spotted high-energy neutrinos created by a particle collider, detecting 153 events with extremely high certainty. This significant milestone in particle physics could help scientists deepen their understanding of highly energetic neutrino interactions in the universe and unravel the secrets of how stars burn and explode into supernovas. Neutrinos are tiny subatomic particles that are found almost everywhere. Every time atomic nuclei combine or break away, neutrinos come into existence. They are produced by cosmic rays and radioactive decay in particle accelerators and nuclear reactors on Earth, and even in a banana, from the natural radioactivity of potassium in the fruit. However, these massless and chargeless particles are the ultimate cosmic ghost. Once produced, they rarely interact with matter. About 100 billion neutrinos pass through each square centimeter of our body every second, but they are so elusive that we can't even feel them. This elusive nature earned them the nickname ghost particles.